So can everyone see my screen? Hello? Okay. Okay, so it's already 10 and I think we can get started. All right. Before I start, I think a few of you emailed me whether we have homework for this week. So we will not, because I think you guys probably need to prepare for the midterm. And if you look at the syllabus, we also have 1 day of break for the basically the Wednesday after the midterm. Okay, so next Wednesday we will not have a class, and we will resume the class contents on next Friday. Okay, so I think for the exam, again, I don't want to stress more about the importance of the homework. Okay, so try to allocate your time more effectively when you prepare the midterm. Okay, so this class we're gonna start a very new topic. Okay, so we spend almost or more than half of the semester talking about particulate matter. And from this class on, we're going to talk about the other criteria of pollutants and the carbon dioxide. So for these gas species, like the gaseous air pollutants, there's one thing that won't give us a headache, that is the size, right? So we know that for the particles, they have different sizes, and for the particles of all specific sizes, we need to come up with a pollution device, right? So we first talk about the gravitational settler, and we realize that the particles may be small and they won't settle down, right? And then we transit to cyclones. The cyclone is still not effective for small particles, and that's why we have the ESP and the backhouse filters. But for these gas species, they don't have a size. So their size is only the size of the molecule, which is typically below 1 nanometer, right? And because of that, when we remove them, we have to rely on some physical or chemical process that's targeting at these gas species. So you'll realize that later on, we're going to talk about the chemical reactions a little bit, and then also the adsorption, which is mainly the gas molecules adhering onto the surface some solids. Okay. So first, let's get a quick overview of the sulfur dioxide. Okay, so we said that the sulfur dioxide is one of the most important air pollutants, right? It is a criteria air pollutant. It is bad because on one hand, it can pose an impact on the human health. And we said that if we inhale the sulfur dioxide, they may need to lead to allergies or asthma, which is bad for people's health, right? And at the same time, we mentioned that for the criteria air pollutants, they're not only important because of human health, right? It's also important because they can cause some damage to the properties or damage to the animal life, plant life, or enjoyment of life, right? So in terms of sulfur dioxide, we said that one of the most important feature is the formation of the acid rain, right? And this is actually also the reason why some historical architectures are turning their color, okay? So if you search on search on some news of Taj Mahal, right? Right, this is a very famous architecture in India. You'll find that the acid rain is turning these architectures from white to yellow, okay? It is not because of the sun, it is because of the acid rain, okay? So we know that for these architectures, they are made of limestones, and the limestone is mainly composed of calcium carbonate. Right, so basically the calcium carbonate can react with the components in the acid rain and further get corroded, right? And then reveal these yellowish color. So I think that the Indian government has clearly realized this issue, and that's why they're also trying really hard to control their air pollutant emission into the atmosphere. Okay, so if we just quickly go over what's happening during the acid rain, right? We know that we emit the sulfur dioxide, right, into the atmosphere, and then they can react with water to form sulfurous acid. Okay, and then the sulfurous acid is actually not very stable, so they can react with oxygen to further get oxidized, right, into sulfuric acid. So the sulfuric acid is a very strong acid. It's also a very stable, right? Stable acid, strong and stable. So what this sulfuric acid can do if you have acid rain and then measure the pH of the rainwater, you can see that the pH can change from the condition where there's no acid rain, right, to the condition where there is acid rain of a value of 4. So if there's no acid rain, if there's no sulfur dioxide, then you normally can see a pH of around 5.5. But if you have sulfur dioxide emitted into the atmosphere, the pH can drop down to 4, which means that the acid is going to react with the calcium carbonate and further basically convert them into carbon dioxide. So you may have a question, why the pH is 5.5? Okay, so we thought that if there's no sulfur dioxide, why shouldn't the rainwater have a pH of 7? So the reason why that's not 7 is because we have carbon dioxide in the air, okay? So the carbon dioxide can also combine with water to form a relatively weaker acid, okay? This is a carbonic acid. Okay, so the carbonic acid generally has a pH of around 5.5, or at least in that buffer system, they tend to have a acidic pH here. But if you further have these stronger and more stable acid like sulfuric acid, then you're going to reduce the pH down to 4. And then what happens is that the calcium carbonate can react with the sulfuric acid to form calcium sulfate plus water, and then carbon dioxide. Okay. So for such a system, the calcium sulfate is less, I would say it's more soluble compared to the limestone and compared to the calcium carbonate. Okay, so this is more soluble. Okay, so if that's more soluble, it means that basically these architectures are getting corroded by the acid, and then you are going to emit carbon dioxide and water into the atmosphere. Okay, so this is why the acid rain is going to pose an impact on all of these properties. And we said that it's not only about the properties, right? The acid rain can also impact and the plant or animals' life. And this is again a picture of the Smoky Mountain. I really like Smoky Mountain, so that's why I put quite many pictures of the view there. So I'm not sure if you have been to there. That's actually a quite amazing place to be, especially right now is the foliage time, right? So if you find some time, have a visit, it's a quite spectacular view in there. So this is a picture taken from the Clemens Dome, which is the highest point in the Smoky Mountain. And again, you can see these hazy views, right? So that's because of the particle being formed just by the vapors emitted by the plants. But what you can also see are these chunks of wood. Okay, this is not because of any disease among the trees or any insects. It is actually because of the acid rain. Okay, so the acid rain is corroding the leaves of the plant and leaving these ecological damage to the forests. Okay, so that's why we have to pay some attention to the sulfur dioxide control. But if you just look at how we have been doing with the sulfur dioxide emission, you can see that actually people are doing a pretty good job. Okay, so here what you can see is this is the emission. So basically the volume of emission in thousands of tons in terms of the sulfur dioxide. Okay, and this is also plotting against time from the 1970s to 2017. And you can see that the sulfur dioxide emission is decreasing very rapidly, right? It's almost like a exponential decrease. So I think we discussed why this is the case in our first class. So just as a quick poll and as a quiz, right? Can you fill in this quiz and see what is the reason for this rapid decrease of sulfur dioxide? Okay, 10 more seconds. Okay, we'll stop here. All right. So the correct answer should be EPA. I know that some of you probably chose the first one because it looks longer. Okay, I said that if there's something that you don't know, you look for the longest answer. But here, I specifically made it EPA, not spelling out the full name. So it is the Environmental Protection Agency that has the regulation or the policy of the sulfur dioxide emission, right? And because of that emission, because of that policy, we start to have this decrease of the sulfur dioxide emission. But this is not reflecting the actual sulfur dioxide concentration. Okay, so these two are different. It is because if you still have a positive emission, it means that if the sulfur dioxide is not being removed by any other mechanisms, the sulfur dioxide concentration will still build up because you're emitting them into the atmosphere, right? So that's why we still have to pay attention to where these sulfur dioxide are coming from and how we can control them. So it turns out that right now, in terms of the major sources of the sulfur dioxide, so 1/3 of it is actually coming out of the oil refinery. Okay, so generally the oil refinery, what they do is they convert the crude oil into some oil products like the gasolines or some other chemicals, right? But the unfortunate thing is that the crude oil has quite a lot of sulfur inside. So they have to deal with that. And some of them can get leaked into our atmosphere. And the other important source, which is the remaining source of the sulfur dioxide, is the coal-fired power plant. And this is because we're burning coal, right? So the coal has sulfur inside, and then we need to deal with the sulfur that's coming out of the combustion process. Okay, so since these two are the major sources of the sulfur dioxide, we also need to design control systems or control methods, right, to remove or limit the emission of the sulfur dioxide. So we'll start with the oil refinery. Okay. So actually, there are two ways to control the sulfur dioxide emission. One way is called the before combustion method. Okay, we also call them as the fuel desulfurization. So we use that in the oil refinery, in the sulfur dioxide control in the oil refinery. So what it basically means is that we will extract the sulfur out of the crude oil. Right. Let's say this is a barrel of crude oil that we got. Right, we send it into the oil refinery, and then we extract the sulfur out of these crude oil, and then make the products and send it to the customers or to the other manufacturers. Okay, and there is another method that's called the after combustion method. Okay, so the after combustion method, what that means is, or a more technical term is called the flue gas desulfurization. Okay, so the flue gas, this is basically the combusted gas or the combusted gas mixture. So everything has already went through chemical reactions, right? When you have already extracted the heat out of the fuel. And when you have the flue gas, we try to get the sulfur dioxide out of it. Okay, so one is before combustion, one is after combustion. And we use the before combustion method, the fuel desulfurization method for the oil refinery, and we'll use the flue gas desulfurization for the coal-fired power plant. Okay, so for these two different emission sources, we have two different control methods. And yes, I saw that Nathaniel raised the hand.
Yeah, I had a question. So like I know that like catalytic converters do a lot for like, catching a lot of pollutants for cars. Does that also catch sulfur dioxide too?
So the catalytic converter is not designed to capture sulfur dioxide. Okay, it's designed to capture VOC, the volatile organic compounds, and also some NOx coming out of combustion. So if you really look at the check the composition of the gasolines, and they just have very little amount of sulfur. Okay, so the reason is when we use these gasoline, they have already been pre-treated by the oil refinery. So the reason behind that is, let's think, if you have the gasoline that still has sulfur inside, then when we burn it, we get sulfur dioxide. And the sulfur dioxide is bad for people's health. So they might lead to some liability issues. Okay, so people may even sue the oil refinery and say, why don't you treat the sulfur and causing the health hazard to people? So that is one of the reasons why people use this fuel desulfurization to remove the sulfur beforehand, before we distribute it to the gas stations. Right? Does that make sense?
Yes, thank you.
Yeah, so by the way, the catalytic converter, we're going to cover that later on when we introduce the VOCs or the nitrogen oxides. So there are some reactions that we need to discuss as well. Okay. And maybe we can just start with the oil refinery. And as Nathan, you just mentioned, right? So why can't we treat the sulfur dioxide after the combustion, right? Why can't we treat those, I mean, from the car emissions, why can't we treat it by a device that we install in the car? We said that it's because we want to treat it beforehand to remove those health issues, potential health issues. And then you may also have the question, why can't we treat the coal just like the gas, just like the oil, right? Just like the oil refineries, we pre-treat the coal. So there are some difficulties to that as well, and we can go over that later on. So first, about the oil refinery. So it turns out that the sulfur is actually the fourth dominant element in the crude oil. So when you know that the oil has the carbon, hydrogen, oxygen, right? And then actually the fourth important one is the sulfur. And we normally use this symbol as the component that has sulfur inside. So basically this is a bond, and the R here represents the organics that doesn't have the oil inside, right? And in terms of the crude oil, people actually grade these crude oil based on the sulfur contents. So if the sulfur content is higher than 0.5%, which is a relatively low amount, right? And people will call them as the sour crude. I think this is a pretty interesting name because the sour means acidic, right? We say that the sulfur will create these acidity because they form sulfuric acid, right? So we call them sour crude. And if the sulfur is below 0.5%, we call them sweet crude. So everyone like sweet things, right? So we enjoy these sweet crude. But it turns out that actually more than 80% of the crude oil we got are sour crude. Okay, it's not very good. So because of that, and also because of the potential health issues, the oil refineries play a pretty important role to remove the sulfur before we distribute them as products. So the method they use is by combining the sulfur containing crude oil with hydrogen. Okay, so there's a reaction happening at high temperature, sometimes high temperature. And then the hydrogen can extract the sulfur out of the crude oil. So you're going to have R and hydrogen sulfide. Okay. So the hydrogen sulfide is pretty toxic, which means that people cannot inhale them in large amount, right? So I would say before the year of 1970, so what the oil refinery do is they basically will react these hydrogen sulfide with oxygen. So they just burn them off, right? Okay, so I saw Mitch posted a question what it means by R. So the R here just means the organic component. So for example, if you have like C6H, H10, and then you have a sulfur on it, right? We'll just treat this C6H10 as R, okay? So basically this is the organic component of the crude oil, all right? Okay, so as I said, before the year of 1970, what the oil refinery do, they generally choose to just burn these off. It's not only burning the hydrogen sulfide, but also some other toxic gas or some trace amount of hydrocarbon, so they can combine all the stream and burn them off. But what happens to the hydrogen sulfide is that through this high temperature reaction, you're going to have water and at the same time, sulfur dioxide, okay? So this is not a way of dealing with air pollution. So this is a classic example of the redistribution or the pollution redistribution. okay? It's not pollution control. So basically, instead of emitting sulfur dioxide by the cars or by the customers, we chose to combine all the sulfur dioxide emitted by the oil refinery, right? So we're not dealing with the air pollution problem at all. So with the establishment of the EPA, people realize that, well, we have to deal with these hydrogen sulfide, okay? So at the same time, deal with the sulfur dioxide, okay? So they just put these chemicals together, right? You list them. You see that here we have some hydrogen. Here we have some oxygen, okay? So with that hydrogen, we can know that hydrogen and oxygen, if they combine, they're going to form water. So can we invent a chemical reaction that produce water, but at the same time combine the sulfur by themselves to form the sulfur solid? And that involves a lot of chemical engineering and finding the correct catalyst to make it work. But indeed, people made that work. And this process here in the oil refinery is called the Claus process. Okay, so people indeed found the method to do that. Okay, so basically you are forming water, right? And at the same time, you form the solid sulfur, and you can use that for some other applications. But more importantly, you dealt with the pollution or the pollutants of the hydrogen sulfide and sulfur dioxide, right? This is a very good example of a two bird, one stone process, right? You deal with the pollutants, but at the same time, you form some chemicals that you can probably use. So you may have the question, well, is that a significant chemical reaction, right? Is that very important? So before we do that, let's first try to balance this equation, right? You're going to have 2 hydrogen sulfide and form 3 sulfurs in here. So it turns out that the sulfur that we generate out of the oil refinery occupies 90% of the sulfur supply in the US. Okay, so this really shows that how much, I would say, how important this chemical reaction is, but at the same time, how much oil refinery, how much oil we use every day. Because in terms of the sulfur application, they can be used in gunpowder. So just think about the weapons we purchase, right? So in the country, right? And also the bullets people manufacture. This is a pretty large market there. And just by the oil refinery, they can cover around 90% of the market. But gunpowder is a little bit violent. If you think about things that are less violent, the fireworks. So fireworks also need sulfur inside, right? So I would say next time, let's say July 4th, right? When you see the fireworks, you know that those sulfur, there's a 90% of chance is coming out of the oil refinery, okay? So this is a very important chemical reaction that can generate a very profitable commodity coming out of it. And of course, we can use the sulfur. Since this is solid sulfur, this is very pure. We can also use that to manufacture some chemicals with very pure requirements. For example, we can form sulfuric acid if you're looking for purity higher than 99.999%, right? So if you need this pure of sulfuric acid, then you have to form it from the scratch, right? You should let the sulfur react with oxygen and hydrogen to form these very pure chemicals. Okay, so that's why for this fuel desulfurization process, I would say the chemical engineering really played a very important role here. So we designed the process that can make this reaction happen, and we solve a major environmental problem here. And then you may have the question, well, can we do that do the same thing to the coal, right? So we have the coal-fired power plant. Can we use the similar reactions to extract the sulfur out of the coal? So if you compare the coal and the crude oil, the major difference is that the oil is in liquid form and the coal is in the solid form. And that is one of the major reasons why we cannot use this Claus process onto the coal particles, because if you have a solid particle or a chunk of material, and then you try to let hydrogen react with it, then it's going to be very difficult for the gas to reach the center of the particle, which means that it's going to be less efficient to remove the sulfur out of it. But if you have a liquid, right, you can generate some liquid fumes or even liquid droplets, right? And for those reactions, it's going to be more efficient to extract the sulfur out of it. So that's why for the coal, people tend to not to use these processes, but instead we deal with the sulfur after we combust all of the coal, okay? And the other reason is that I would say the customers will not buy coal for themselves, typically will not do that. So the coal is still quite centralized in the coal-fired power plant. And because of that, we can build some air pollution control devices to directly capture these sulfur dioxide coming out of the system, okay? So this is, I would say, the major difference between the fuel desulfurization and flue gas desulfurization. And we covered these fuel desulfurization here. So in terms of the flue gas desulfurization, so what happens is, let's say you have the combustor, you have the coal inside, right? You have the flame, and then after you get all the combusted gas, right, you will first send it through some particle control devices, and then send it to a what people call a scrubber. Okay, so in the scrubber, we're going to remove the sulfur dioxide through some chemical reactions, and then you can emit it to the stack. So this is a more conventional way of designing the sulfur dioxide control by using the scrubber. So I think in your team project, you're going to design a dry sorbent injection method or a dry particle injection method, which is a little bit different compared to the configuration here. But we call these processes as the flue gas desulfurization or the FGD method, okay? So basically, well, if we have this method, so how many power plants are using this method to remove the sulfur dioxide? So here I'm showing a distribution of all the coal-fired power plants we're right now having in the United States. You can see that there are quite many dots, and the size of these dots represents how much sulfur dioxide they emit. Okay, so you can see that at least in the year of 2010, not a lot of power plants are using the FGD system. You see a lot of these red dots here, which means that they don't have FGD, while the green ones have the FGD. Okay, so the blue ones means that they are planning for FGD systems. You can see a lot of coal-fired power plants, and they're big emitters, right, as well. So hopefully these power plants are changing their attitude and plan to build these sulfur dioxide treatment systems so that we're emitting less sulfur dioxide into the atmosphere, right? So because if you see the distribution here, still 2/3 of the sulfur dioxide is still coming out of the coal-fired power plants. So how do they work? Okay, so there are different types of the flue gas desulfurization systems. For example, you could have the limestone scrubbing, right? So the limestone scrubbing is basically the process where you introduce the limestone as droplets. So you dissolve or try to dissolve some of these calcium carbonate or mix them with water to form kinds of like a slurry. And then in a reactor, let's say this is our reactor here. So in the reactor, you're going to introduce the flue gas that contains the sulfur dioxide into the reactor. While at the same time, you have those spray nozzles to spray the droplet that contains first water and calcium carbonate. So the calcium carbonate, we know that it's made of it's a major component of limestone. They're not very soluble. So that's why we have to grind them into fine particles and then try to mix them with water. And within each droplet, basically you're going to have these calcium carbonate, and then the sulfur dioxide is going to react with the calcium carbonate, right? So basically you have this reaction taking place. So you'll first form calcium sulfide, and then you will form basically the carbon dioxide. Okay, so in this way, basically you can capture, at least you can remove the sulfur dioxide out of the flue gas, and then form this chemical here. And then at the bottom of the reactor, you're going to have a liquid reservoir, right? And in the liquid reservoir here, we're going to introduce oxygen. So basically, this is not a stable chemical yet, right? You're going to let that get further oxidized. Into calcium sulfate. So the calcium sulfate is going to be more stable. And then we could use them as the gypsum, and then further to let's say in terms of construction, they consume a lot of gypsum, right? So we can further use them in those processes. So here I have a short video to show you how the limestone scrubbing works. So maybe we can take a look here.
In some instances, sulfur dioxide from combustion is removed from the flue gases by using it either to produce sulfuric acid or gypsum for construction. These products can then be sold to help offset the cost of running the flue gas desulfurization plant. In both cases, oxygen is used to help encourage the necessary reactions that need to take place. In the case of sulfuric acid, adding excess air to the sulfur dioxide and vanadium oxide converts it to sulfur trioxide, SO3. When combined with water, this produces H2SO4, or sulfuric acid. In the case of gypsum, limestone slurry used in wet scrubbing processes combines with sulfur dioxide to produce calcium sulfite. When subjected to a forced oxidation process involving the addition of water and oxygen, the sulfite is converted into gypsum. In addition to these processes, oxygen is also required in flue gas desulfurization processes using seawater. As the seawater absorbs the sulfur dioxide, oxygen is added, creating a mix of sulfate ions and hydrogen, which in turn converts to water and CO2 gas. In all three cases, using an oxygen probe to accurately measure oxygen concentrations can help to regulate the conversion of sulfur dioxide.
For more information about ABB's AZ analyzer range, contact your local
So this is a short video about the chemical processes that involved in the limestone scrubbing. So here is another one. This is probably more common to the coal-fired power plants.
In the absorber, flue gas mixes with water and limestone. The limestone reacts with and removes about 98% of sulfur dioxide, creating the byproduct of gypsum. The wet flue gas exits out the top of the absorber through to the wet stack and a gypsum slurry stream is pulled from the bottom of the absorber and sent through a dewatering facility. Inside the dewatering facility, most of the moisture is removed from the gypsum so it can be sold for use in wallboard.
Okay, so basically the scrubber here is the process that we can use to start to share my screen first. Okay, so I got it back. Yeah, so the scrubber system is basically the process where we can extract the sulfur dioxide coming out of the coal-fired power plant, right? So first we will form the calcium sulfide. And since calcium sulfide is not stable enough, right, we're going to further introduce oxygen, right? Kinds of like bubbling oxygen to the solution that were collected at the bottom, right? And to further form the calcium sulfate. So the calcium sulfate is minorly soluble in water, but most of them will still precipitate. Okay, so the most common state is actually the solid phase, which means that in this liquid reservoir here, at the bottom, we're going to be able to collect all of these calcium sulfate and further dewater them and form the gypsum. Okay, so there are some other processes that can deal with the sulfur dioxide. For example, instead of using the limestone, you could use lime, right? So you could have the lime scrubbing. So the advantage for lime scrubbing is that the lime is mainly made of calcium hydroxide, which is a strong base, right? So in this way, you don't have to try to dissolve these solids into water anymore, because the calcium hydroxide itself is soluble. So the reaction here is going to be more complete and the efficiency is going to be better. Okay, so we could also have the lime spray drying. So what the spray drying means is that we're still going to have these spray nozzles at the top, but the difference is instead of making a liquid reservoir at the bottom, so what we can do is that we can make these droplet size smaller so that when they fall down, they're going to evaporate. So basically, there's going to be nothing that's collected at the bottom. Instead, these dried particles, these reactive particles, are just going to flow with the flue gas and then exit from the top of the scrubber. Okay, so one thing probably I forgot to draw in here is an outlet. Okay, so the flue gas still have to exit from the scrubber. Okay, although the sulfur dioxide is removed, you still have a lot of burned gas species like carbon dioxide, water, and some others, and nitrogen, of course, right? So basically, from the scrubber is the process where you have the gas phase reactions and getting them collected, and then form some products out of it, or at least form some other solids out of it, right? And I think that maybe you're interested in this direct injection method. I think in your team project, we're going to deal with either the trona injection or lime injection. So what this direct injection means is that we're just going to remove all of these nozzle here. So there's no water involved anymore. So what happens is, if let's say this is our duct that's transporting the, for example, the flue gas. So instead of introducing any liquid into the duct, we are just going to introduce a solid, okay? Introducing these solid as particles. So you're going to have either lime particles or trona particles. So all the reactions are going to take place on the solids. If we just zoom in into this solid here, right? You're going to have a solid particle, and then you have sulfur dioxide on it. And sulfur dioxide is going to react with either trona or lime. So we said that the lime is made of calcium hydroxide, right? Or the trona is mainly made of the sodium carbonate or sodium bicarbonate. So there are going to be corresponding reactions between the trona or lime and the sulfur dioxide. Okay, so in this way, basically you're forming these products. You're removing the sulfur dioxide, and then just get the product still in the state of solid. Right, you're going to basically introduce some particulate matter into the flue gas, so that the reaction can happen. So now, if you think about it, so we said that the coal-fired power plant need to remove the particulate matter, right? So if that's the case, for the dry injection here, we probably have to put it before the particle removal devices, right? So if I just draw the combustor again, right? Think about the entire process. For example, this is our combustor, right? It's forming a lot of pollutants. At the same time, you're burning these particles here. So out of this combustor, you're going to transport the flue gas outside, right? So there can be some heat exchangers, or there can be some nitrogen control devices. Oh, okay. So I saw Nathan, you just raised hand again. So are you talking about the black box in there?
Yeah, that's what I was about to tell you.
I think it's probably the panel for the videos.
Oh,
yeah. So
okay.
what about now?
I don't see a black box in the lower corner, but now I just see a black
did you
box in the
guys-
middle of the screen.
Yeah, do you guys miss anything when I write things?
No, it was I think we just didn't see some of the SO2s there. But
Okay.
you know, nothing too significant, but I wanted to make sure you know before you wrote something over there.
Yeah. Thanks for putting in the chat and raising hand. Okay. So what I'm trying to say is that for the dry injection and the limestone scrubbing, we have to consider the sequence between the PM removal and the sulfur dioxide removal.
Dr. Wong,
Yes.
I do see a big black box in the middle of the screen now.
Okay. What about now?
All right, yeah, no, we're good now.
Okay, yeah. So we're trying to basically find out what's the sequence for the PM removal and sulfur dioxide removal. Okay, so for the dry injection, since we're introducing the particles into the duct, right? Introducing these either trona or lime particles, so we're still getting some particles out, right? So it means that it's going to be more effective if we just do the dry injection first. And then send it to the PM control devices, either cyclones or ESP or filter, right? And then we put it through the exhaust. But if you think about the limestone scrubbing, so what the limestone scrubbing is means is that we're going to introduce these flue gas through these spray of droplets, right? If we want to form some pure products, like the gypsum at the bottom, it means that we cannot introduce particulate matter inside. If you put particulate matter inside, it's like a typical scrubber where you're basically going to contaminate the products we get, okay? So in that case, if you're using the limestone scrubbing or use the lime scrubbing, so everything before is still the same. You have the combustor, right? And then you probably want to do the PM control first. And then let it go through the scrubbing or scrubber. And then let it go through the stack, okay? So basically from the PM control processes, we remove all of those particles inside, so that when the flue gas is introduced into the scrubber, you don't introduce particles anymore, and the products you get out of the device is going to be have a pure component, right? It's going to be a better quality in terms of the gypsum. But if you use the dry sorbent injection or the direct injection method, then we don't have the requirement for the product anymore, right? But instead, you're introducing particulate matter inside. And if you still use this method, you deal with PM, but here for the dry injection, you still introduce particles, but there's no way to control them anymore, right? So that's why we need to put the injection before the PM control devices so that we can deal with all the particulate matter in once, right? So any questions? So we're going to talk about these limestone scrubbing in more details in our next class. I think that's going to be Friday. Okay, so in the meantime, if you have any questions about the exam or about the team projects, you can feel free to ask me. I think that's it for this class. All right, thank you for your attention.
I have a question real quick.
Yes.
Is the class next Friday, is that going to be online or in person?
Yeah, that's going to be online too.
Okay, cool.
Yeah.
Thank you.
Yeah.